All right, so we're going to continue our discussion of rotation, okay, and forces, and I guess we're going to combine them together. So we're talking again about uniform circular motion, and so far we know this relationship where if you take the velocity of an object divided by the radius, the square, and divide by the radius, you get centripetal acceleration. And we know that there's a relationship here between velocity and the period and the circumference of a circle. Okay, and we're going to add to these relationships now. So really we're going to focus on what it means to have centripetal acceleration and the causes of centripetal acceleration. And so when we have a system that is balanced, then the sum of the forces adds to be 0, and that system moves at a constant speed or is at rest. Okay? If we have a system that's unbalanced, then the sum of the forces adds to be the mass times the acceleration, which means that the velocity of the system is changing. Okay? And so in this certain special case, when we have uniform circular motion, the sum of the forces then is going to add to be m times centripetal acceleration. Okay, and so these are for objects that are moving in a circle. In those particular special cases, then the sum of the force adds to be m times centripetal acceleration. And so we call this the centripetal force. Okay. So that's called centripetal force, and it can also be written as mv squared over r. Okay, and so this is for the special case of uniform circular motion. And so for this one, we're going to do a quick example. We're going to think of think of the Earth, okay? And so whenever you're moving in a circle, then the sum of your forces has to be equal to mv squared over r. Because, and then we call this the centripetal force, as I said. And so if your centripetal force, or if the net force acting on you is greater than this amount, then what's going to happen is you won't be moving in a circle anymore. Then you probably would be spiraling into the center of the circle or falling out of the circle. And if the value of this was less than Fc, your centripetal force, then you would be leaving the circle. Okay? And so there's an exact balance that has to take place for there to be circular motion. And so let me give you an example. So like, let's say that we're standing on the Earth. Okay, so here's the Earth. Here's a person. And while we say that this person isn't moving, they're actually having acceleration because they're moving in a circle. Okay, so they're experiencing uniform circular motion. And so traditionally we say, well, they're balanced and they have a upward normal force and their downward weight, mg. Okay, but technically this is not equal to 0 because they're in rotation. It's equal to mv squared over r. So mv squared over r is equal to the normal force minus their weight. And so the normal force, which is the force the Earth pushes them up with, would then be equal to, and I set this up wrong real quick. When we're doing uniform circular motion, we're always going to say that positive is in the direction of the center of the circle. So then, since the normal force is pushing them away from the center, this would be negative, and since gravity is pushing towards the center, this would be positive. Okay? So then, when we do some quick math here, we get that the normal force is equal to mg minus mv squared over r. Which means that because the Earth is spinning, the Earth doesn't have to push up on you quite as hard, which means that like when you step on a scale, the reading you get is actually slightly less than what your technical like real weight would be. And so if the Earth were to stop spinning and this would be equal to 0, then you would weigh slightly more. Okay? But let's think about this real quick. The R of the Earth's radius is really, really big, whereas the velocity of the Earth is relatively small. Okay, which means that all of this is much smaller than mg. It's much smaller than your weight. The amount of unbalance basically is what it is. And so this basically goes to 0. And that's why we say that normal force is equal to mg. But let's say the Earth were to spin faster and faster and faster to the point that we couldn't say this. The faster the Earth would spin, the less the Earth's surface has to push up on you to keep you in place. And you can imagine that the Earth spun fast enough at some point that v squared over r was equal to g, in which point the normal force acting on you would then be equal to 0. And at that point, you would technically be orbiting the Earth. Okay, so what you want to think about with circular motion is, at any moment, your velocity is tangent to the circle. Okay, and then the force is kind of pulling you back into the circle. Okay, so if you're going fast enough, then like the faster you go, the less work the circle has to do to pull you inward, because you're kind of already moving that way. Okay, and then you get to a point where you're moving so fast that you're actually going to escape, like, or I guess the force has to work harder. You go so fast that the force can't pull you in hard enough, and so you just escape the circle. Okay, let's look at another example of this. So like if you think of like, if you have like a yo-yo, okay, and you're spinning it in a circle. Let's say it is a 1 meter yo-yo, or has a 1 meter radius. Let's say it has a mass of 0.2 kilograms. Okay, and we're spinning it in a circle. Let's say that the velocity of it is, we'll say it completes a rotation in 1/10 of a second. Well, we'll just make up a number. Let's say the velocity is 15 meters per second. Okay, so when the yo-yo is at the bottom of the circle, we have weight pulling it downward, and we have tension pulling it upward. Okay, and up will be positive because that's the direction of the center of the circle. So this is at the bottom. But when the yo-yo is at the top, you then have weight pulling down, and now if it's spinning at this top point right here, it's getting pulled downward by the string too. So you also have downward tension at the top. And at this point, we're going to say down is positive because always we're saying towards the center of the circle is positive. So this would be at the top. And so we're going to think about this in terms of the amount of tension that is in the string. Okay, so think about it. Where does the string have to work harder, at the bottom of the circle or at the top? When you're spinning a yo-yo, it has to work harder at the bottom, and I'll show you why. So for this equation, we're going to say it's having rotation, which means centripetal force, which means mv squared over r. And we're going to say, okay, we have positive t going to the center minus mg going away. So in this case, t is equal to mv squared over r minus mg. Okay? Or sorry, plus mg. So t is having to account for the difference, or the total centripetal force that has to be applied, and the weight of the object. So it's having to work extra hard to keep it in rotation at the bottom. At the top, on the other hand, if we write this equation, it's mv squared over r is equal to, now they're both positive because they're both downward, w plus t, so that t is equal to mv squared over r minus w. So you can see tension now is being helped by gravity to keep the yo-yo in rotation. Okay? And so this is kind of the basics of rotation. Okay, we'll get into this more in some of the practice in class, and then we'll do some more practice on the next video.